Imagine a world hidden from our everyday sight. This world is not in distant galaxies. It exists deep inside the tiniest particles. We are talking about the heart of the atom. This is the realm of nuclear physics. It's a branch of science full of wonder. It explores the atomic nucleus, its strange rules, and the immense energies locked within. Nuclear physics seeks to answer big questions. What are the fundamental building blocks of matter? How do these tiny pieces interact with each other? What powers the stars that shine so brightly? The answers lie in understanding the nucleus. This field is relatively young yet so profound. It has dramatically reshaped our world. Its discoveries continue to amaze us all. Think about the sheer scale of things. The nucleus is incredibly small, fantastically dense. If an atom were the size of a football stadium, the nucleus would be just a tiny marble. Yet almost all the atom's mass is there. This tiny speck holds unbelievable power. It's a place where familiar laws bend. New forces come into play here. So, let us embark on a journey into this subatomic universe. We will explore its fundamental particles. We will learn about its governing forces. We'll see how its discovery changed history and how it impacts our lives today, from energy that lights our cities to medicine that saves precious lives. Everything around you is made of atoms. The chair you are sitting on, it's atoms. The air you are currently breathing, atoms. You yourself are a collection of atoms. These are the fundamental building blocks of matter. For centuries, they were thought to be indivisible. The word atom even means uncuttable. But we now know there's more to their story. Atoms are incredibly tiny structures indeed, far too small to see with any normal microscope. Millions could fit on the head of a pin, yet they are complex little worlds themselves. Each atom has a central part. This is called the nucleus, which is dense. Around this nucleus, electrons whiz about, like tiny planets orbiting a miniature sun. The electrons are negatively charged particles. They are very light and move incredibly fast. Their arrangement determines an element's chemistry, how it bonds with other atoms, for instance. But the real heart of the atom is its nucleus. This is where nuclear physics truly begins. The nucleus is positively charged overall. It contains much heavier particles. So an atom isn't just empty space. It's a dynamic system, buzzing with activity. Most of its volume is indeed surprisingly empty. But its core, the nucleus, is packed. Understanding this structure is key. It helps us understand all of existence, from the smallest quark to the largest galaxy. The atom holds so many universal secrets. Let's zoom in, past the orbiting electrons. We arrive at the atom's very core. This is the nucleus, small yet mighty. It was discovered just over a century ago, but it holds profound secrets about matter. The nucleus contains two main types of particles. These are known as protons and neutrons. Together, they are called nucleons. Protons carry a positive electrical charge. The number of protons defines an element. 1 proton means it is hydrogen. 6 protons make it carbon, essential for life. 92 protons make it uranium, a heavy element. Protons are fundamental to an atom's identity. They are relatively heavy particles, much heavier than the light electrons. Neutrons, as their name might suggest, are neutral. They carry no electrical charge at all. They have a mass very similar to protons. Neutrons play a crucial role in the nucleus. They help to bind the nucleus together. Without them, most nuclei would simply fly apart. The number of neutrons can vary in an element. This gives rise to what we call isotopes. So, the nucleus is a dense bundle, a collection of positive protons and neutral neutrons. It's incredibly tiny, as we've said before, about 100,000 times smaller than the atom itself. Yet it accounts for over 99.9% of the atom's mass. Imagine squeezing a car into a sugar cube. That gives you an idea of its density. This tiny, dense core is where the real nuclear action happens. We have protons packed tightly in the nucleus. All these protons have a positive charge, and we know that like charges repel. So what stops them from flying apart violently? There must be another force at play, a force much stronger than electromagnetism here. This incredible force is called the strong nuclear force. It's one of nature's fundamental forces. The strong nuclear force is truly remarkable. It is the most powerful force we know. Over incredibly short distances, it dominates. The distance is found within the nucleus itself. It acts like an immensely strong cosmic glue. It binds protons and neutrons together tightly. Without it, atomic nuclei could not exist, and therefore, matter as we know it couldn't exist. This force has some very peculiar properties. It only works over extremely short ranges, roughly the diameter of a proton or neutron. If nucleons are too far apart, it vanishes, but when they are close, it is overwhelming. It affects both protons and neutrons equally. Neutrons essentially add more strong glue to the mix. This helps to stabilize the nucleus. The balance between forces is delicate. The strong force pulls nucleons together. The electromagnetic force pushes protons apart. In stable nuclei, the strong force wins, but in very large nuclei with many protons, the electromagnetic repulsion becomes significant. It can stretch the nucleus, making it unstable. This instability leads to nuclear phenomena like radioactivity. Section 5. Whispers from the Unseen, the Dawn of Radioactivity. Our journey into the nucleus began unexpectedly. It started with mysterious rays from certain rocks. In 1896, Henri Becquerel made a discovery. He found that uranium salts emitted strange energy. This energy could pass through opaque objects. It could even fog photographic plates in the dark. This was the first hint of radioactivity, a sign that atoms were not so stable after all. Soon after, Marie Curie and Pierre Curie stepped in. They were pioneering scientists, full of curiosity. They investigated these mysterious uranium rays. Marie Curie coined the term radioactivity. She suspected other elements might be radioactive too. Their painstaking work was truly groundbreaking. They processed tons of pitchblende ore. This was to isolate these new active substances. Their efforts led to incredible discoveries. They found two new elements, polonium and radium. These elements were far more radioactive than uranium. Radium, in particular, glowed faintly in the dark. It continuously emitted heat and penetrating rays. This was astonishing, a source of endless energy. It challenged the physics of the time. It suggested the atom had an internal structure. These early discoveries opened a new window into the subatomic world. Scientists realized that some atoms were unstable. They spontaneously transformed into other atoms. In this process, they released energy as radiation. This radiation came in different forms. Alpha, beta, and gamma rays were identified. The study of radioactivity paved the way for nuclear physics. Section 6. Cracking the Code: Key Milestones and Brilliant Minds. The discovery of radioactivity was just the start. The early 20th century was a golden age. Many brilliant minds worked to unlock the atom. Ernest Rutherford was a key figure here. In 1911, his famous gold foil experiment took place. He fired tiny alpha particles at thin gold foil. Most passed straight through as expected, but some bounced back, which was a shock. Rutherford famously said it was like firing a shell, a 15-inch shell at a piece of tissue paper, and having it come back and hit you. This meant the atom was mostly empty space, but it had a tiny, dense, positive core. This was the discovery of the atomic nucleus. It completely changed our model of the atom. The atom was no longer a plum pudding. Later, in 1932, another crucial piece was found. James Chadwick, Rutherford student, discovered the neutron. This explained the missing mass in the nucleus. It also explained isotopes more clearly. Then in 1938, a monumental discovery occurred. Otto Hahn and Fritz Strassmann in Germany were bombarding uranium with neutrons. They found lighter elements, like barium, appearing. Lisa Meitner and Otto Frisch, working together, correctly interpreted these startling results. The uranium nucleus was actually splitting. They called this process nuclear fission. They also calculated the enormous energy released. This discovery was truly world-changing. It opened the door to nuclear energy, but also to the terrifying power of atomic weapons. Section 7. Harnessing the atom nuclear power explained. Nuclear fission releases a tremendous amount of energy. This comes from converting a tiny bit of mass, converting it directly into energy, as Einstein predicted. E equals mc squared, his famous equation, explains this. A small amount of mass, m, times the speed of light squared, c squared. This equals a huge amount of energy, E. Nuclear power plants harness this process. They use controlled chain reactions of fission. Inside a nuclear reactor, uranium fuel is used, often in the form of uranium oxide pellets. When a neutron strikes a uranium-235 nucleus, it can cause that nucleus to split. This releases more neutrons and lots of heat. These new neutrons can then cause more fissions. This creates a self-sustaining chain reaction. If uncontrolled, it leads to an explosion. However, in a power plant, this is controlled. Control rods, made of neutron-absorbing materials, are inserted or withdrawn from the reactor core. This regulates the rate of fission reactions. The heat generated by fission boils water. This creates steam, just like in coal plants. The steam then spins turbines connected to generators. These generators produce electricity for our homes. Nuclear power has significant advantages. It produces very few greenhouse gas emissions. This makes it a cleaner alternative to fossil fuels. It also has a very high power density. A small amount of fuel produces a lot of energy. However, there are challenges too. Managing radioactive waste is a major concern. Ensuring the safety of reactors is paramount. Section 8. The healing atom. Nuclear physics in medicine. Beyond energy, nuclear physics plays a vital role in medicine. Its applications are saving lives every single day. This field is known as nuclear medicine. It uses small amounts of radioactive materials. These are called radiopharmaceuticals or tracers. They help to diagnose and treat various diseases, especially cancer and heart conditions. It's a powerful tool for doctors. One major application is medical imaging. Techniques like PET scans, positron emission tomography, and SPECT scans, single photon emission computed tomography. These allow doctors to see inside the body. They can observe how organs are functioning. A patient ingests or is injected with a tracer. This tracer emits radiation as it travels. Detectors then create images of the radiation. These images provide unique information. They can detect diseases in their early stages, often before symptoms even appear clearly. For example, PET scans can show cancer cells. Because cancer cells often consume more glucose, a tracer attached to glucose will accumulate there. This helps in accurate diagnosis and staging, allowing for more effective treatment planning. Nuclear physics is also used in cancer treatment. This is known as radiation therapy or radiotherapy. High-energy radiation is precisely targeted. It aims to damage or destroy cancer cells. This can be delivered from an external machine, or by placing radioactive sources inside the body. Techniques are constantly improving, making treatments more effective and reducing side effects. Section 9. Our nuclear future challenges and amazing possibilities. The journey of nuclear physics is far from over. Scientists are constantly pushing the boundaries. exploring new frontiers of this amazing science. One huge area of research is nuclear fusion. This is the process that powers our sun. It involves fusing light atomic nuclei together, like hydrogen isotopes, to form heavier nuclei. This releases even more energy than fission. Fusion power holds incredible promise for humanity. Its fuel, like deuterium from seawater, is abundant. It would produce very little long-lived radioactive waste. And the risk of a runaway chain reaction is nil. However, achieving controlled fusion is extremely hard. It requires incredibly high temperatures and pressures, like those found in the core of a star. International projects like ITER are working on it. Beyond energy, fundamental research continues. Scientists use particle accelerators to study nuclei. They are probing the nature of quarks and gluons, the building blocks of protons and neutrons. They are searching for new particles and forces, trying to understand the universe's origins and the mysteries of dark matter and dark energy. Nuclear physics is key to these grand quests. Of course, with great power comes responsibility. The legacy of nuclear weapons reminds us of this. The safe management of nuclear waste is crucial. Preventing nuclear proliferation is essential work. We must use this knowledge wisely and ethically for the benefit of all humankind. The future of nuclear physics is bright, filled with challenges but also amazing possibilities.